Okay. So, when we last met, we were about to watch a video. Can you hear it?
Very softly. Can you make it louder?
It's at maximum loud. It's very loud here.
Concerning pointing devices for use on mixed keyboard and typing tasks.
Can you hear this?
Only a little. Hardly. Very soft.
Okay. Would you like me to pause this and just talk then?
Or you can narrate it. We can see the video.
All right. Gosh. Okay.
Or if you can't figure out a way of making it louder.
It's well, if I make it, it's all the way to 100%. You can't turn yours up, huh?
Well, yours sound fine.
Notice the 10 is not technical guide all work behind the mouse.
Hey, we aren't taking our hands off the keyboard. That's the whole point. So my hand is already where it needs to make decisions and selections while I'm texting to them.
There are only to a mouse. We'll present an argument.
So the real, I think I should just give, well, there's my laboratory. So we use strain gauges on the sides of this thing. You can see those paddles or switches so we could evaluate where to put the buttons. We put the, our idea was to put the pointing device between the two hands, because your hand always is typing on JKL semicolon and ASDF, but not between them, not between P and A, with hands crossed. Now what he's holding right there is a sensor that goes underneath the J key. And we had this idea of putting it under the J key and just wiggling the J. Now that was an interesting idea because, of course, it takes no change. The problem is you have to figure out how to teach a person about it, and you also have to make sure that you get rid of any J that you typed when you're planning on making a selection with that key instead. And we tried putting it below the space bar. In fact, my first idea was to use a pad back in 1983 or something. But your thumb, it's very hard to remember to use your thumb as a pointing device. So the idea is that this thing, if it's small, maybe it'll be okay in space. And we've been playing with lots of them. This is a 1990 video. This is the first time I really showed it publicly. And you see, we're using this target practice. Right there, the way we test it is to see how long it takes her to make a selection in that circle. And there's a couple of different things we did around that circle. One is the size of the circle. When it's small, of course, it's harder to select, and the distance also shows that it makes it harder to select. So we're plotting here difficulty, which is Fitt's law, which is the distance over the size. And by doing that, we were able to see that by changing certain things about the transfer function, we were able to make a better, blue one is a better pointing device. That means that the more difficulty it gets as it goes out on the Y, on the x-axis, the less time it takes compared to earlier pointing devices. What's surprising about this algorithm, that's the blue line, and we'll talk about it more later, is that people have been trying to make rate control devices for decades. Actually, there was a paper in the 1890s about how when people tried to select a position by changing the rate and then stopping, they overshoot. And that's the key thing that we learned, is how not to overshoot when you're making selections. So this graph is kind of us playing with that. And the idea, let's see, I don't know how much more this video is going to be fun, but you can hear me okay?
Yeah, we can hear fine.
I can't hear you at all. Oh, yeah. So this is a more similar to selecting text experiment. We use this to test our different rate control selections all the time. And really the difference in our protocol for testing joysticks from other people is underlined by this experiment. Because we would basically run this experiment, change the rate control function, and then run it again. And it's like a 30-second task to select all of these characters. And the point is that we could compare transfer functions for their performance rather than for their than how they felt. So the thing that people have done before, people like Snoop, Hard, everybody, had done is made joysticks that felt good to make selections with. And what we really tried to do was test them not how well they felt, but how fast they were to make selections. This is Joe designing transfer functions, and we had a piecewise way of designing these transfer functions. And what we found was that you'll see this plateau, and then you'll see on the right-hand side, I should pause it and go back and show you that. Right here, we are, the edge of this transfer function is going up. And what was interesting is we found that people could go make selections much more quickly by limiting how fast the track point went. But people didn't like it going so slow. So we put on this thing we call turbocharge. I'll talk more about that later. But what's interesting about the turbocharge is that in those selection experiments that I was showing, where we selected 16 letters all over the screen, people did not do better with that turbocharge. And so we didn't understand why people like to go zooming around with that turbocharge. And indeed, other people that had made pointing devices always had made them zoom around. And in the end, I tell you that zooming around is the way to drive a Ferrari off of a curve. In other words, people like transfer functions that were more responsive in this control. However, there's a very interesting story about this turbocharge, which is that we thought people liked it. We didn't know why, until 6 months later when we realized that people were using that to change contexts. So the interesting thing about going fast is you can change from one window at one part of the screen to another window at another part of the screen in a few tens of milliseconds. That becomes exciting. And that saves people a lot of work when you're changing tasks. So there's several things that we do with a pointing device. We might make some accurate selection. Maybe we're trying to pick a pixel. Maybe we're trying to pick a target, if it's a button. Maybe we're trying to move something. Steering law, something that Jun Tsai named, is when you have to hold on to something, like moving it through a path. And for each of these different tasks, of course, there's different constraints on what our muscle memory can do and what controls we have. I'll talk a little bit more about that in a minute. Let's see if we can finish this video.
Ongoing research includes exploring more precise experimental paradigms for helping us understand.
So what's kind of amazing is that transfer function I just showed you gives about 25% faster selection than any joystick algorithm that anyone had ever shown in the literature before. And so when we started discovering that plateau was like that, the circle experiment that you saw that woman doing earlier, where you have a circle of different size, and that circle gets small to make it difficult, or far away to be difficult. Now, we were able to use that to figure out how much force control a person has. And what we discovered was that people only have about 5 bits of force control. That means 1 in 32 selections. And so when we were designing the transfer function, this came in extremely handy. What we realized is that for making pixel by pixel selections, that wasn't enough control to actually make those selections. Let's see if we can turn to. All right, we are going to go into a presentation where I'm not fighting with the video. I'm going to turn up the volume so I can hear you guys better. I'm sorry that volume was too low. Can you guys all hear me now?
Yeah.
So what this was inspired by was that I was reading a book back in 1983 or 4 that was written by 2 guys, Tom Moran and Stuart Card. And this was the first human-computer interaction text that was available. And it was a pretty interesting book. And one thing that I found interesting in this book was that there was some very old, interesting research where Doug English and Engelbart had, Tom English and Doug Engelbart had done an experiment when they just started making this device that turned into the mouse. Actually, Doug Engelbart made something that had 2 wheels perpendicular to each other. One would scrape along while the other would roll and move this device around on the table. It's actually a very uncomfortable device, but it was the first mouse, so that when you pushed one way, one wheel would roll, and when you pushed the other way, the other wheel would roll on the table. And they were comparing this to a variety of devices, like cursor keys, or like a knee bar. A knee bar is something that is used by sewing machines. You push your knee against it and it goes faster. And what was really interesting about the data is I had heard about this experiment, but I'd never seen that for the first 15 minutes of the data, the knee bar was faster at selecting things than anything else. And I kind of wondered what that was, and I realized about a page later that it takes almost a second to take your hand off the keyboard and put it on a mouse, and about a little bit less than that to put it back on the keyboard. So this is almost 2 seconds, over 1 3/4 seconds of time to make that. So if you're bad at using a mouse, because you've been learning, because the learning curve, how you haven't gone up the learning curve, or cursor keys, and you're bad at using a knee bar, at least you're not taking your hands off the keyboard. And that attributed all of the improvement for text editing with this knee bar, which went away after a few minutes. By the way, just last year I asked Mr. English, I was at a party and I told him, I found this data in your paper that showed me that the knee bar was better than a mouse at the beginning. He said, it was not. And I tried to discuss it with him, I couldn't. The thing that's interesting about that for me is how a lot of times you will find that people make an interpretation out of their experiments, and they come up with data that they believe in and teaches them why something was important. And in fact, after they've made that interpretation, they don't really need to think about it again. And so they don't. And they miss some very good things. And there are lots of examples of where you can read other people's papers and learn more from those papers than other people have. And I really encourage you to do that. So in any case, I thought, well, I could take this problem of having to take the hand away from the keyboard and put a pad underneath the keyboard. You see these pads today. Those pads existed in 1980 in the Apollo computer, made in Pittsburgh actually, in the Perth. But they have problems. Your hand, it's very uncomfortable to use your thumb as a pointing device, even though your thumb is a very, very sensitive, very dexterous thing. So I watched people trying to use their thumb, and what they did is they found themselves taking the finger off of the keyboard and putting it down in the pad area. So they still took their hand off the keyboard. So that's why I said, oh my God, maybe I can put the pointing device underneath the J key. That's the home key for the right hand. That would be using the most dexterous finger we have to make selections. And as I said earlier, the problem with that was that when you did that, you were trying to decide whether I was typing a J or making a playing selection. We figured out how to take away the J if you held the key down, and how to use other buttons for selection, but we didn't like that as much as just having an identifiable separate device that you could make selections with. The next problem that we found, of course, is that the joystick in that position between the G and the H, where I showed you earlier, as it was in the last that last keyboard, this one here, actually is where the finger is fattest. If you put your finger on a key, you'll see that the pad is the biggest at the center of the key. And later on, you'll see in all of the pointing devices that are on your keyboards that have track points, that the mouse button is moved below the G, above the B, and the H, so that it actually is where the pad of the finger is smaller. Another thing that's interesting about this picture is that thing is a rod, and we had convinced ourselves that a thin rod was necessary so you would touch it, and we made later on little cup-shaped things that would grab your fingerprint, and these things were about 1/8 of an inch in diameter. We thought they were wonderful. We convinced ourselves that a soft top was somehow going to lose control. And actually, that's an interesting story, which is that we found ourselves going to Japan at a time when there was somebody using a trackball. There was a human factors guy. He convinced himself that the trackball was better. He was working very hard with Alps, making trackballs. And we went over, and he gave a talk where he showed how the trackball was better than the track point in every in the first 45 seconds of use. So he had this whole spreadsheet showing how basically if you use the track point in different situations, it was always better except for the first minute that you were using it. And when I pointed that out to him, that was the beginning of a very important conversation, which ended up getting track point into product. But I'm getting ahead of myself. The thing that was interesting about this man is he wanted compliance. Now, the finger can feel muscle motion. All of our muscles have this secondary muscle fiber that has a neuron wrapped around it and goes to the backbone, and it helps you know how far you've moved your finger. And so when you have that feedback, it gives you more information. So he thought that if we had the feedback of emotion, it would make people make better selection. What we were worried about is, of course, how do you get motion in that little tiny space? And I literally tried probably 50 different things. I used sorbitane, cork, and sandpaper, and foam, and finally I made a top that had just a little bit of compliance. It was a ping pong paddle top with a little bit very modified, and then a 55 barometer post, and just could move a little teeny bit. And what we found, which was very exciting, was that while experts didn't improve, novices improved by 15%. Now, just to keep that in context, when input device takes 5% less time to make selection, everyone notices it immediately. So that was a big, big deal. And in fact, that made him happy, which made him want to put it into the product. So he made a contribution. But also we did find that moving the key down, the track point down between the G, H, and B, between the G and H, was another way to get it out of people's way without making it just thinner. The overshoot problems I already talked about. I'll say a little bit more about it. And what's surprising also is I thought this was the smallest, stupidest project I'd ever worked on. I was working on adaptive health at that time, AI and education, AI and user interface, a topic that Brad has worked on for decades as well. But in fact, it took about 8 years to get this to work. So the real trick was figuring out how to make a top that was grippy and would not be uncomfortable. The first ones were so uncomfortable they put dents in your finger. And we'll talk about drag buttons in a minute. But the thing that is shown in this picture is not the first three things I said about transfer function, which is we found making a predictable slow speed in the transfer function made another 15% performance improvement for making pixel by pixel selections. In other words, if you can't control, with that 5 bits of selection, if you can't control how fast the cursor is going, it goes at a specific speed, then we are in better position to stop at the right moment. So that's that 15%. Making the transfer function so that it didn't go too fast, and we found out that plateau, remember I talked about that plateau, when you go too fast, it doesn't lose control. And that's the story about a Ferrari going off the road. It turns out that what that plateau is it's the eye tracking speed. So if you don't go faster than your eyes have to track the pointing device, then you don't have to go look for it and find it again. And that is the thing that, like I said, for 100 years people were talking about things overshooting and having to find them again. So that plateaus for that. The turbocharge is for doing big selections. We thought we were great. That's how we went to market in 1993 with a product called the ThinkPad 700. It made a huge impact. Everyone loved it. They've been selling the same amount of display, same amount of battery, same amount of processor, and couldn't sell even 10,000 of them. And then they put in the track point, and they sold $500 million of them in the first year, $500 million worth of them in the first year, $1 billion in the second year. So that was the only change from the pointing from the notebook computer before to the one we saw that we had the track point in. It was the track point, same size display, everything. So that's why they gave me some resources at IBM. But suddenly I was making their product succeed. We kept working on it, and there's a whole lot of stories about improvement, but one of the funny ones is on this page, which is, I thought, how do we get a selection to where we want faster? Usually you really are just going directly to it. What if I just make it to the fact that you're going towards it, we kind of keep it going in that direction? Well, that's called hysteresis. And in fact, it's terrible, because when something keeps going in the direction you want, put the rudder in and turn it, it's hard to hit a mark. Well, so we did the opposite, and I call it ABS brakes and negative inertia. So the point is, when the track point senses you trying to go faster, it goes much faster. But it only goes faster enough that you can still track it with your eye. So that is the negative inertia for starting, and for stopping, we see you trying to stop it, we stop it faster than you could do with your muscle control. The plateau gave it about 20-25% performance improvement over other joysticks that people have made, and the negative inertia another 10-15%. And then for specific things like going fast and going slow, we have other algorithms. And so there's more actually, but what I want you to think about is really a cognitive model, a model of the user and what their abilities are, their physiological abilities and their perceptual abilities. And by putting those abilities into the design, we're able to overcome a lot of the limitations of control that people had thought were innate. So much so that in the year that I published that video that you saw, 1990, there was a paper by Stuart Card, a dear friend of mine, huge hero, hopefully he'll come talk to you, which said that linear transfer functions were better than nonlinear transfer functions for all input devices. Now, that was given at Interact 90, and at the same conference I showed a video, I had a paper, and I had a demo. And all three of those showed him incorrect. We had a hard time. For me and Stu Card, it was several years before I actually tracked him down in a mall, chased him with a computer open with my experiment on my laptop, and made him go through my pointing selection task that you saw on that screen. And after doing that for a few minutes, he decided that maybe I was right. Maybe transfer functions didn't have to be linear. Maybe they could have a cognitive model in them. This screen is especially interesting because each of these lines, the 10-minute, 40-minute, 1 week, 3 minutes, they come from experiments done by people in different places. So at the time that we were trying to get this into product, there was a group in Yamato, Japan. And as I told you, they showed that the track point for select and type was no better than a pad or a trackball. Well, they only tested it for 3 minutes in that experiment that they reported on. The people in Lexington, Kentucky, they had an experiment to test it for 10 minutes. They showed that, yes, it was 15% better than a trackball or a pad, but not better than a mouse. Well, it is better than a mouse already. No, it's worse than a mouse. But what we found was if you let a person spend 40 minutes making selections carefully, they can actually outperform a mouse for point and select. Now, point and select is you're typing and then you select, typing and then you select. That's not just making selections over and over and over again. In fact, for that, I don't have the graph up. You see it, you continue to get that. And then this is the track point 3 with the negative inertia. These ones are all track point 2. What's interesting about a mouse is I used to think it was a terrible device. Man, you can draw with rock, with what somebody used to say about the fact that people use mice. But in fact, what's really special about a mouse is that you can put the heel of your hand down on a surface. Well, anyway, while you're using it, and just use your fingers to move it around. Or you can lift it up and use your whole arm to move it around. So in that way, you're able to use different motor control for different purposes. And in fact, people can make selections with, over and over again with a mouse in 0.9 seconds, no problem. You can do that with a track point, but I'm just saying that it's a very, very impressive device, a mouse actually, in spite of what we think. The other thing that's special about a mouse, I can talk about it with devices all day, I'll move back to track point, but is it doesn't fall over. So at one point I patented the stylus. You'd hold a stylus and you'd let go and it wouldn't fall over. And that I think would be better than a mouse, because when you're holding a stylus, a pen or something, you are enlisting a lot more muscles and grouping them that you don't get to enlist when you're grabbing something like a mouse on the top. And I believe there's still lots and lots of room to make pointing devices better with the ergonomic issues, with the cognitive issues that I was showing you, and also you'll see with application-dependent issues. So one problem that happened when we were showing this thing off to a very famous industrial designer that had a lot of control at IBM for design, a guy named Richard Sapper, is he took this track point, he tried to draw a circle, and it wouldn't draw a circle. Well, it wouldn't draw a circle because we had made it good at doing text selection. So it was good at going horizontal and vertical. And of course he was right, and we went back and tried to make a circle. Now, the righteous way to do all that would be to have, when you're in a graphics application, it's optimized for making anisotropic motions, and when you're in text, it's good for making vertical and horizontal selection. But we didn't have that luxury. We didn't have control over the drivers, and when we had to make driver changes to computers to use our devices, we found that people didn't load the drivers and they decided to like it. So trying to make it work perfectly, regardless of the application, was our initial goal, what was required to get it out the door as an actual product for IBM. There's a lot of other things that happen. I'm going to give play an audio. Oh shoot! I hope you can hear this. It's an audio from space. all of the spacemen in our country anyway use TrackPoint. And they use it because it didn't float away. They use it because, well, let's see what they say. Let's see if this audio.
It's actually a lot easier to type on the mouse than it is. I think it's a lot easier to get to the one that's type on the computer too. And I think that type that before. I make a whole lot less mistakes people work on than I did earlier. So I know that was a joystick to use. Yeah, it's really simple to use. I never thought I'd be talking this way about a computer, I'll tell you that.
Okay, so I don't know, could you hear anything there?
Yeah, a little.
Okay, so basically, the first time it went up into space in a shuttle, they were just loving it, and they were talking in about 3 minutes, and that made me really happy. But anyway, the thing is, I started off thinking that the cool idea would be to put this in normal keyboards, and everyone would use it. In fact, a company called Chase Manhattan wanted to put it in their cubicles for their tellers because they thought it would be take less space than having a mouse next to them, and real estate in downtown areas where they have people to take your money at banks was expensive. IBM did not find that a big enough market area, and so we did not start by making those keyboards. We started by making the ThinkPad. And the reason that they were able to make a decision to put in a ThinkPad was that we did not have a competitive advantage. Our ThinkPads were not able to sell, compete with Apple or anybody else. And by putting that in, we gave it a competitive advantage. So that was the reason that they chose that. Later, they did put, they made keyboards with these in them. You saw them at airports. Sometimes you still see them. United used to use them for a long time. Toshiba, Zenith, Sony, HP all use TrackPoints. Dell put one in, but they made their buttons very stiff, and when you make the buttons stiff, it will reduce your ability to make selections by huge amounts, and that's another story. We thought about using it for a variety of things, and in the end, it could be used for anything. It could be used for remote controls. If you did have only one button on your remote control for controlling your television, and the menu became a pie menu that came up on the screen. Does everybody know what a pie menu is?
Yeah, we went through that.
Yeah. Then you could, up and down is volume, side to side is channel, diagonal is features. And you could have one button so that you're in the dark having had some beers. You don't have to look at 30 buttons on your remote control. I made a air traffic control TrackPoint. Air traffic controllers were just moving to using computers at that time, and they hated keyboards. They didn't want to use the computers to control airplanes because of that. So I put a TrackPoint on a handle, and it allowed them, and I made a very special, actually patented switch that allowed them to talk to the airplane or the voice echo. And it kept IBM working on, kept the contract for the air traffic control for IBM because they had this funny thing. I couldn't find the picture this morning. I'll talk a little bit about it. We put a TrackPoint on a laparoscope for Johns Hopkins University. That was really fun because when we did that, they were able to control their camera inside of a person's body while they were in surgery with their thumb. And the reason this works was because built into that transfer function is a variety of things that get rid of tremor. So the negative inertia and some other things about the TrackPoint allow that to work. And one of my favorite moments is Brad Myers can tell you that there was this man who just died last year named John McCarthy. He's an incredible guy. He invented Lisp, he invented AI, he coined the term AI. He was a friend of ours. He, one day, the first time he got to use the TrackPoint, we were in the back of a recreational vehicle with the man who invented swapping, a guy named Fred. And John wanted to try it out. So he started playing solitaire. Well, John was well known to have a tremor. His hands were always shaking. And I was terrified. We're in the back of a vehicle driving, and he's trying to use the brand new pointing devices. You know, who knows if it works for him. And what was amazing is he was able to play solitaire perfectly. And it's because several things about the algorithm reduce the amount of noise caused by tremor for a person trying to make selections. So that really impressed me. And then that surgical device was a great thing to do. We didn't go to market with it, just too busy doing everything else. Sightless pointing, another big surprise. We found that when we showed this to people who are blind, they loved it because it was in one place all the time. And so it helped them. And there was a major marketing manager, actually vice president at IBM, who had lost both of his arms. And he loved it because it was easier to control than a mouse with metal claws. We found that people with mouth sticks, people that had quadriplegics, that had a mouth stick that they wiggle around the world, tap on keys, they liked it because, like I said, this transfer function made it easier to make precise, controlled selections than with other control devices. So they liked it. Besides, it was stable in this device. So these were all surprises to me. We also found some improvements for steering that it needs for dragging because it doesn't change its speed in ways that are, it allows control at slow and high speeds. Two-handed pointing, we'll talk about a little bit. Anyway, you can use them for lots of things, but specifically, we made a lot of different devices. This is the remote control for a television. We were playing around with two. This is a microphone for people doing radiologists making notations on X-rays, and then we tried making it into a mouse, and I could talk about that a little bit later. One of the things that bothers, every time you make anything, there are problems. And the first computers that have this in it, how are we doing for time, Brad?
Fine, you have until 10 to 3, about another half hour.
Okay, so this is how they were set up. You see that there's only like about a ½ inch, 3/4 of an inch in front of the space bar before you run out of computer. And what I was absolutely sure of and learned with my experiments is that if you had a place to rest the palm of your hand, that you could have better control with your fingers. And so I fought like crazy for a wrist rest. And it was impossible to get a wrist rest into our products. And so from 1993 to 1996, we didn't have one. And this was one of my solutions, trying to talk them into it. This is that black part you see is just a membrane. And all this, these little ridges are to fit between the keys so that you can make it fit in the keyboard when the computer's closed. And when you open it up, you unfold it, and this little latch goes on that little tab and makes this funny shape that snaps on the front of the computer, making a wrist rest. Now, I believe that designing and making this wrist rest that could stow in a computer, which was a tremendous amount of mechanical engineering you can imagine, to make that thing stiff and strong and snap right onto a normal computer and let you rest your wrists on it, was the turning point for the product team. And it's hard to believe it now when you look at your laptops, but back in 1996, no laptop had space for your hands to rest on it. And that made a big improvement for our pointing device also. You'll see these half-rounded buttons. There they are. Those were the way that the track point came out originally, and I hated those. The curvature was very, being so high, it actually put a lot of pressure on your fingers. So I explored lots of different kinds of buttons. And this one down here, believe it or not, we patented this. This is one with a lot of space on it, and it went into a set of products from 1995 to 97. And what's special about this one is you see these red dots. This is to let a person that has a mouth stick or otherwise has only one hand to turn on the mouse button without, and lock it into position. So this is press and lock. Went to product to help people with disabilities. And that was one of the ways I got a smaller diameter, a bigger pad, was to design this thing. So it helped everyone by having a bigger mouse button, and it helped people that had only one hand by letting them lock the button in place for drag. You'll see that it morphed into something else. Now, let me just say something about what you're seeing here. This is a very strange track point. That track point has that circle in the center, which is I'll show one here maybe. This is a magnet. You can probably even hear it. There's a magnet that can pop up and down in this one. So I wanted to make a haptic feedback track point in the products. And that would be that you could have force feedback to show you when you went over the mouse, the edge of a window, when you went in, when you made a selection, you could feel it on the tip of your finger. And we had lots of fun making those. The first one I made, I wanted to make it free, so the way I designed it was to finger and have a low-pass filter and have a big excursion voice coil in the speaker, but I put a piece of plastic on top of the voice coil, and then it would, when it came up high enough, it'd poke a little stick, which would poke through the track point and tap your finger. We made that work. It was fabulous. What was surprising to me is when we tried with blind people, whether they liked a little toothpick pricking their finger through the red top, or whether they liked the whole dome pricking their finger. What do you think they liked better? The blind people, the people that were used to using their fingers to touch the world. Did they want the little prick, or did they want the big round top that went up and down slowly, or went up and down altogether? I need an answer. Brad, what do you think?
Well, somebody said the round one.
Okay, so it turns out that they like the print. They like the precise feeling of the little pin, which was not what I expected. Instead of the big round thing popping up and that was interesting to me. We tried making them piezoelectrics. We blew up lots of computers for high voltage. They didn't have the excursion. We tried a lot of things. We had a lot, and finally we designed them that were so small it would fit right in the post. 50 cents extra. We couldn't get the product to go. Oh, here's why we couldn't get it to go to market. Is I proved that it made you learn how to use the pointing device faster. But once you learned, it didn't make you go faster. So you could make selections more quickly when you're just starting out. But after you got used to the track point, the feed forward, just being able to go to where you wanted without the haptic feedback was just as good. And so I told them that, and maybe I'm too honest, and it didn't go to market, so we don't have half the track points. You see in this picture here, one of these haptic pointing devices. This particular handle I designed to go with a wearable computer that I was building at the time. Now, here is an interesting thing. Why 2 and why in those positions, okay? And if you go and type, you'll find when you go and take your finger from the F down to the space bar, or the J down to the space bar, or you take your thumb up to make the space bar, is how we really do it. You don't cross between that line. You're always using the space bar with the thumb, or that with your finger. So this device over here was a fabulous idea. I thought we were going to go to market with 2 pointing devices there. Anyway, we did experiments. We found out that sure enough, you could do 3D controlling. Barton Smith and I, and I think Schumann may have been on that paper. I wrote a paper about how you could use 2 devices, kind of like driving a tractor. One goes forward and you turn them around, or the other one goes forward, you go through that way, you pull them out to go down, or up, in to go up. That was great. But what was really surprising was when I made 2 devices that were asymmetrical, I had a different experience than making them symmetrical. And does anybody have any idea about what the difference in, if you made them asymmetrical, two devices versus symmetrical might be? Just a guess.
Maybe it's easier to not get them confused because you're not only.
What was that?
So she said maybe it's easier to get them not to be confused with each other?
Well, what's interesting is that when they were symmetrical, it was hard to remember which one did what action. And when they were asymmetrical, it was very easy to remember which one did what action. And it has to do with there's this symmetry in the brain. In fact, Brad can tell you about this keyboard that's called a half-QWERTY keyboard, where you can actually type with your right hand as though it was your left hand. If you think about it, it's very easy to type an S with your ring finger on your right hand. That is how our brains work, is that they're very good at symmetries. And there's a guy making, I don't know what's his name, somebody in Toronto makes these keyboards where you make the left and the right in one with the same keys. Your index finger does F or J. But anyway, when I made these into asymmetrical, we were much better at making selections. And we use one of them to zoom and the other one to select. So that's one thing you can do with two, is you zoom, select, and zoom and select. And that is actually built into today's track point. You can go into a mode for making it a magnifier. You can go for press to select. We got rid of this button here by making the track point have 3D capability by having more strain gauges. We got rid of temperature compensation, but we also were able to get vertical, so that a person that has a prosthetic or a single hand or something, they can push down to make select, press to select. It can be a little distracting for your me to use, but press to select got rid of the need for these lockout switches. And then I was really hoping that we could have multiple track points in the keyboard, and I showed that it had performance improvement. You could do making selections of very precise things, like going around a Google map or something, much better. But what we did instead, which you'll see in today's computers, is this button down here. And this button down here allows you, when you press that button, actually you'll see the middle button on yours, it goes into scroll mode. And that is actually the second button. That's what so that lets you select with one hand, and they set something up with one hand and do it with the other hand, which is what we typically do with our left and right hand. We use one hand to set up a problem, the other one for performance. So that was really fun. So really, all of our explorations in two track points turned into this third button. We find in every track point today. Unlike a scroll mouse, you can go in two dimensions, not just in one. So you can go diagonally and stuff. The bad news is that the drivers are fighting us, and you'll find that sometimes when drivers do funny things, it's hard to use that feature. This is one more thing about this button. Notice these little dots. Without those dots, people could not tell whether they were on this button or that button. So that was one of my major contributions. And these little triangles of tape were part of the exploration to show that we needed to have texture on this button to distinguish it from that button. This tube comes off another track point. And it's really fun. That tube, when you close the lid of a laptop, it goes down. And what that tube is for is you can grab it with your hand and you can use it as a stylus, so you can write signatures and stuff. And I wanted so badly to put a stylus in our devices. I put, anyway, a lot of effort into that. It could have happened. Finally, I left IBM to go to MIT and stopped changing. They stopped changing the track points at all. This was one of the last things that I did. I used to run around with my laptop had this keyboard in it, and I could write signatures really well with that nice dexterity that I would tell you to have with all 45 muscles all grouped together trying to do something. But even the texture of this thing matters. And you'll see this top here is a different top than these. These tops back here are rough. Now those weren't the first tops either. The first top, there's a great story about it. What happened was that I had made that special ping pong paddle rubber that I believed was so important to making the grippiness. We actually got performance improvement by having good grippy top. And they wanted to make a plastic top with little bits of rubber in it because they want to save money, and they was going to go to the market with that. And it wasn't very good. You'd have to press harder to do it. Pressing harder is no good because, well, in fact, you know, the stress in your hands and RSI is something, repetitive strain injury, something we don't want. And that's one of the goals of this thing, was to give you an alternative to mouse for the level of strain injury. So, as they were going to product with this not so grippy top, I actually engaged my father to help me design. He worked for the Bureau of Standards on rubber back in the Second World War, to design a rubber top that was extra grippy. And we did. We made a really good rubber top, and it wasn't going to be ready for the product. But we talked them into letting me make the tool engine. And what's interesting is about 10 days after the first product was shipped in 1993, the top started breaking, those plastic tops, because people were pressing on them so hard, they smushed themselves right off the top. And so right then we were ready with our rubber top. It was 480 little grippy top, and we put it onto all the product. People loved them. They were very sticky. It was lovely. But about a year later, we found that they were expanding because they absorbed oil from people's fingers. And at that point, we went ahead, and I don't know how much detail you need to know, but this grippy top here was the outgrowth of a whole lot of research. The grippiness, that little pieces of nylon embedded in the top, about the frequency, spatial frequency of your fingerprint. And why that's kind of got made is, first I made some ridges that were the size of the fingerprint, then I made little Velcro-y things that stuck up, little nails your finger went on, and I was trying all sorts of ways of making the grip be based on mechanical rather than any stiction. And I went over to Japan, and these guys had taken a fish skin. Now Japan likes fish skin. They found that was so sticky. I'd never felt anything so sticky before. And I didn't know why it was so sticky until I looked at it under a microscope, and it was because it had these little things pricking up. We didn't want to kill a lot of fish, so this is our artificial fish top. This is the next one. And then I had always wanted a bigger top. We were scared of making the bigger top because it took up space. We were worried, I told you before. But in this space, over time, we've realized that people weren't getting it, and we made a bigger top. And this bigger top is a great thing. It gives people better control. By the way, in making these pointing devices, I always made another place to plug in a mouse. And there was a patent on a really cute idea. I don't know that any of the product does it anymore. But the idea was, whereas Apple, when you plugged in a mouse, if you had two mice plugged in, they both work, but if one moved, the other one, it would move the cursor. In mine, the last one that moved it, the track point or the mouse, would have control for 1/3 of a second, which I figured was about conversational speed. So it allowed people to keep control over the thing on the screen and collaborate using two pointing devices plugged into the same computer. And that was, I'm not sure if that's still true. It isn't, because we don't plug in mice to the PS2 mouse controller anymore, and the software for the USB mouse driver isn't there to do that. But just to show you, one of the things I tried to do to show off the 16-bit AV converter that was in there was I made a wand that you plugged into the top of a track point. Here it is. That could let a person perform a lot of science experiments. It was a scale, it was a micrometer, and there was that. Another thing we did to make a Russian tea mouse was this little top, you see that little line there. You could pull off a little track point and Velcro it onto the handle of your wheelchair, or you could hold it in your hand, or you could hold it in that base. And so I thought that we have this pointing device available for lots of different products for people to do things with. We didn't. In designing it, we started off with $35 a piece strain gauges, and to go to market, I found I had to discover a way to make that post for only $12, which was by using constant hand strain gauges and getting them specially manufactured. I don't have a picture of that now here, but each time the product came out, every 8-9 months, I would try to make it cheaper. And one example that I'm really proud of is this piece of ceramic. This piece of ceramic has little pastes on the bottom that are the ceramic strain gauge, and it's using the circuit board as its mechanical frame. And this thing got rid of this long wire that made a lot of signal problems in the product and made it be no wire, going right to the chip. And so this thing cost, in the end, well, that post cost $1 instead of $12. So the whole price of this thing, let's just say the price of that cable was also $2, so it got rid of that. This was a big improvement to make it all in one. And I'm only telling you that because sometimes the fact of getting something to product requires you to do engineering that is completely separate from these cognitive models of user interface. However, built into this track point being there is lack of noise. And in the first product, when it first came out, I was in Madison Avenue in New York City when we announced the product, and about a third of the pointing devices went faster to the left than the right. And I was terrified. What was going on? I took all of those machines off of stage and went back and got some ones that worked, and I found out somebody put a big capacitor in the feedback loop because they didn't want the noise because of this long cable. And that meant that the bisection sword, the software that was doing the calibration, was actually not settling before it made a decision, so that it was calibrating incorrectly. Anyway, we fixed that problem barely, but by making such a track point that has a much smaller, has no cable, we got rid of that noise problem, we got rid of cost problems, we made a more sensitive pointing device, and by being that diaphragm instead of a post that went up, we could do 3D, so I was talking about press to select. In fact, what people don't realize is built into the microphone of this thing is a gesture language. You can do up and to the left, up and to the right, down to the bottom, down to the left, down to the below. So that was in there too. And you'll just see all of these stories of trying all these things. It had to do with the fact that at every step, when you're putting something new into product, people resent it and they don't want it to happen, and you find yourself having to overcome even more obstacles. Here's a picture of me with that science wand showing, pendulum with this quarters of pendulum, so it has a resonance and frequency. I'd use this in a swing to show acceleration. I'd use it as a lot of other things. As time went on, my graphical user interface work got used in this graphical language for helping people open up and take out the computer from the ThinkPad box. This graphic, I don't want to go into too much, but this graphical interface is a huge damn thing. This got rid of $13 of packaging because we had this box, and we had this paper, and we had all these things because people couldn't find anything on their track form. And so, on a ThinkPad, so I designed that. I think they've stopped using this picture finally in the last year or two. But in any case, I guess I wanted to just say that there's a little bit more to say, and then I'll open up for questions. I was so annoyed with this one-dimensional scrolling device that Microsoft made that I thought, why can't we make here we have another one, a wiggling top that would allow you to go not just back and forth, but side to side. And one of the things that Bill Buxton said about this when he saw it, he says that a trackball is an RSI enhancing device because you have to go walking along to go forward, right? You have to keep stroking it. Whereas this pointing device that I put in here, not as a pointing device, but as a scrolling device, all of my 2 track points, or the middle button the blue button that I've been talking about, allows you to go in 2 dimensions. And in fact, we wrote a paper about it and showed that it was a 30% faster than the wheel for scrolling, and the people liked that. And we took that to Microsoft, and Microsoft said, yeah, but people are used to buying our scroll mouse, and we don't really want to sell IBM things. So there are lots of reasons that things don't succeed, and we went to market with this special mouse that scrolls, and we were so proud of it. But unfortunately, Microsoft took H-Scroll and B-Scroll out of their operating system just then, so that we couldn't use it without a driver. Without a driver, it's just a lump on top of the mouse, and people have to remember to load the driver, and they don't. And so you probably have never seen the scroll mouse, the device that IBM made that was a scrolling mouse. They made several generations of them. So in the end, making things that matter is a combination of the scientific, having insights, trying them out, learning about the problems other people have had, and then solving them hopefully simply. You might ask what some of the steps are in doing such a thing, and this is a list that I made about that. I just want to say, for those that are skeptical, the reason that the track point isn't seen so much on computers anymore is that IBM was very aware how much money they were making by having this differentiator. So for the first 2 years when we were making it in 1994, they refused to sell it to anybody, and everybody came to visit IBM to talk about it, Zenith and IBM and Sanyo and Fujitsu and HP and Dell and everybody, but we wouldn't sell it. And so there was a variety of things happening. One was a bunch of people made crappy ones, made track points that didn't work very well. You find that in Dell today still. And other people used trackpad because they couldn't get the track point. And even though the trackpad is 20% slower, people got used to it. And one thing to remember about any user interface experience, a man named Lou Gerstner asked me this question once. Lou was the CEO of IBM at the time, very impressive man. He asked me, I was showing him these new user interface techniques, and he said, Ted, these are all really great, but aren't we mostly better at doing things we already know how to do? And I think that's always a real question, whether you want to invest the learning curve to take up a new task, even though it's going to help you 25% faster than a trackpad to do text editing while you're selecting while you're text editing, or whether you're going to just sink back into taking your hand off the keyboard and wiggling the finger around on this pad that has all sorts of affordances and dot types. In any case, I think I'll leave you with kind of this list that I thought that it was a 6-week project to make this pointing device, and it took 8 years to get to the product, because when you think you have an invention, the idea of putting something in between the hand and the keyboard, that's great, but you have to design something that people can understand, then you have to write something about it so that they can remember about it, and you make up mock-ups. The first one I made was actually at Atari Corporation. I made an eraser head thing that was playing around with a potentiometer for the pointing device. When I made one that was really great, after we made one that was really, really good, my boss, Ashok Chandra, very important friend of mine, said, why don't you make 100 of them? And I thought, why would I want to make 100 of these? So before I go to product, so I started making them, and sure enough, after making 3 and handing them out to people, I found out lots of problems that I didn't know. For example, that rod hurt people's fingers, and was in the middle of the keyboard, and also other things. And so each time I made 3 or 4 of them, I'd find myself making them differently. So by the time we'd made almost 100, we learned hundreds of things, I think. After that, by the way, we made some prototypes that worked and got people to try them out. They had temperature control problems, and then we improved those. But what we found also in getting them to go to manufacturing is these things had to be able, you had to be able to drop something 20 pounds onto the top of this thing 10 times. Very tough to make something that strong. And there's a whole lot of things that went wrong in learning about that. I told you a couple of the manufacturing problems with rubber, with the timing of the bisection sort. There's a whole bunch more that we learned going to manufacturing. The splash only worked because the press liked it. If the press hadn't realized that we had these plastic tops and told people bad things about them, you probably wouldn't know about this thing today. The differentiability was huge. That was the big thing it had. Sales went through the roof. That was great. But you know, even a year and a half later, at one point, we made a top, a little rubber top that had too much sulfur in it. And that sulfur in the top, it evaporated, it corroded the strain gauges. We had a bunch of them go bad from that. So there's always problems, and one of the funniest stories from that time was when my brother got one of the first ones, and he called up and said, it doesn't work. And they said, well, that's not a pointing device, that's something to keep the keyboard from hurting the display. It's because they forgot to load the track point drivers in the first 1,000 machines that they shipped. So the market size was great. Warranty problems, I told you, always are, you know, I can tell you more stories about that. Recall problems with the string, with that sulfur in the rubber. Profitability was really great for IBM, but because they didn't sell to other people, it kind of makes the ThinkPad kind of a lone ranger, and it's not a real. The people that love it, and they buy ThinkPads for that purpose, but they don't. But other people don't crave it anymore because they're used to the pad. Extensibility and follow-ons. You saw that I tried lots and lots of things that could be follow-ons. If we had a longer talk or another time, I could show you dozens of other innovations I put in ThinkPad that were a lot of fun. But anyway, I made this big long list partially just to kind of give you the feeling that it's a path. To make anything matter is a long, long path. And if you don't shut me up, Brad, I'm going to start talking about.
No, I'm afraid we do have to stop. I'm sorry we had such a delay to get started, but they have other classes that we get to.
Yeah, there's a question back there.
Anybody have any quick questions you want to ask? Okay, sorry, we ran out of time. Let's thank Ted for talking to us.
Hopefully that was it.
Do you want to send me your slides? I'll put them where the students can find them.
Sure. And I'd love to just, have a moment with you, maybe later or whatever, just to talk about it.
Okay. Thanks a lot. I'm going to hang up.
Take care. Goodbye.